Simplifying radical expressions. There's two main properties we're going to use to do this. One's called the product rule. Product means to multiply, and the quotient rule, which means to divide. Now what these really mean is if you have multiplication and or division, you can always combine multiplication or division. You can also separate multiplication and division. We're going to do both. For right now, we're going to multiply first. So what that means is, if you look at the property, when you're multiplying, they both must have the same index. So when we look at the square root of 3 times the square root of 5, since they're both square roots, we can go ahead and multiply those underneath one square root. What that means is, I'm going to write down the one square root as I have, and take the radicands, 3 and 5, we'll multiply those, 3 times 5. And 3 times 5 is 15. So the square root of 3 times the square root of 5 is the square root of 15. Only because they have the same indices, or same radicals. Now for B part, you'll notice they're both cube roots. So I'm going to go ahead and multiply those underneath one cube root. So I'm going to find the cube root of 4 times 2, which is the cube root of 8. But now I'm going to think, do I know what the cube root of 8 is? And I do, because it simplifies as 2. 8's a perfect cube, or yeah, 8's a perfect cube of 2. 15 wasn't a perfect square, so I left it as it is. Now, for the quotient rule examples, I've actually been doing these a little bit in previous videos, and so here's the reason why. It's because of the quotient rule. So when I see the square root of 36 over 49, what I'm going to do is to separate those, each with their own square root. So I'm going to rewrite it as the square root of 36 over the square root of 49. And what is the square root of 36? Well, that's 6. What's the square root of 49? That's 7. So the answer is 6 over 7. Now I can do that with any radical. And so in this case, B part is the fourth root. So I'm going to rewrite each of these with its own fourth root. So it'll be the fourth root of 81 over the fourth root of x to the 8th. I'm going to simplify each of those, as I have been in previous videos. What's the fourth root of 81? The answer is 3. What's the fourth root of x to the 8th? Well, how many times is 4 going to 8? Twice. And we're done. I'm not going to assume, I'm going to assume that all variables are positive real numbers, so I don't have to worry about absolute values. And so that's going to be the case from now on. I'm going to assume that all variables are positive real numbers, so I don't have to worry about absolute value answers. Now, the big issue that we're going to deal with is simplifying radicals. What we want to do is find the largest perfect square factor that divides into the radicand, and then we're going to rewrite the radicand using that perfect square factor, and then we're going to take that one out. Now, it sounds kind of complicated, but it's actually not. The main thing is we're going to use this product rule, and we're also going to have to remember the fact that a squared of b is the same as a times the square root of b. We're going to do some examples to help you understand what's going on. So we're not finding decimals. Keep that in mind. This is not simplifying or evaluating by finding decimals. This is simplifying by removing perfect square factors. So when we look at square root of 40, there's no number squared that gives us 40. That's a nice number, that is. And so we're going to think, what are all the numbers that can divide into 40, and what's the largest number that's a perfect square? Now when you think of perfect squares, you think of numbers like, I could use a 1, I could use 0, but really you're going to start thinking 2 squared is 4, 3 squared is 9, 4 squared is 16, and so on, so on, so on. Now these numbers get big really quickly, so be aware. So what I'm going to do is, one approach is actually just to take that 40 and start listing all the factors of 40. So you do 1 and 40, you do 2 and 20, 3 won't go, 4 goes 10 times, and 5 and 8. Now one of those is a perfect square. If I had more than one, I'd use the biggest, but only one of those is a perfect square, and that's the 4. So what that means is I'm going to take that 40 and rewrite it as 4 times 10. And then what I'm going to do is I'm going to use the product rule and rewrite that as the square root of 4 times the square root of 10, because they each get their own square root. Now I always write this perfect square number first. The reason being is it helps you understand how to write the answer, or the final answer. Then we find the square root of the perfect squared number. In this case, the square root of 4 is 2, and square root of 10 stays. Now, the better you know your times tables, the faster these are going to be. For example, when you look at the square root of 18, if you know your times tables, you know your perfect square numbers, you'll know that 9 goes in 18. You could also do this. You could also take your list of perfect square factors and start thinking, which of these, what's the biggest number divided into 18? Does 4 go? No. Does 9 go? Yes. 16? No. 25 is too big, so 9 is the biggest one. So what that means is, I'm going to rewrite 18, or square root of 18 as the square root of 9 times 2, because 9 times 2 is 18, and 9 is a perfect square. So I'm going to separate it, each with its own square root, and find the square root of 9, which is 3, and the other number stays underneath the square root, and we get 3 square root of 2. Now there's a faster way of doing these. If you ever seen the Oscar-winning movie Mad Max Beyond Thunderdome, you may have heard the phrase, 2 men enter, 1 man leaves. Well, that's what's going on here. 2 men enter, or 2 numbers enter, and 1 man leaves. In this case, one of the numbers has to be a perfect square, and that's the number that leaves. To show you that, before I do the square root of 80, I'm going to do a little bit of one that's maybe a little bit easier to do. Let's just do the square root of, I'm trying to think of small numbers that you can get. Square root of 20. Square root of 20. If you think about it, 4 is the biggest number that divides into 20. That's a perfect square. So that's the same as square root of 4 times 5. 2 men enter. Guess which one leaves? The 4 is going to leave because the square root of 4 is 2. 5 stays. 2 men enter, 1 man leaves. That's like doing that. 80 is a little different. And the reason why 80 is different is because it has more than one perfect square factor. In fact, let's list all the possible pairs of factors for 80. So we got 1 and 80, 2 and 40, 3 won't go, 4 goes 20 times, 5 and 16, 8 and 10. Now if you look, 4 is perfect square, but so is 16. So if you use 5 times 16, you got nothing to worry about. But let's just say that you don't. Let's just say that you're thinking, using your list of perfect squares, and seeing which one divides into 80. Let's say you come up with 4 times 20. Let's just say, what else? So you wrote 80 as 4 times 20. And you know that 4 comes out as a 2, because the square root of 4 is 2, and 20 stays. Well, you're not done, because the 20 also has a perfect square factor. So we gotta simplify 20, because that's the same as 4 times 5. We just did that one. Now the square root of 4 comes out as a 2, and the 5 stays. Now, up here you'll notice that a square root of b is the same as a times square root of b. And what that means is, this is 2 times the square root of 5. And 2 times 2 is 4. So we end up with 4 square root of 5, which is the correct answer. But let's just say that you realize that 16 was the biggest one, the biggest perfect square factor of 80. And so instead of using 4 times 20, you used 16 times 5, which is what you want to do. And the reason being is the 16 comes out as a 4, and the 5 stays. Same answer, fewer steps if you use the biggest one. It's not wrong if you use the smallest, it just requires more steps. So always use the biggest if you can find it. That's my suggestion for the day. So now let's do D part. I'm going to separate these using the quotient rule, so it becomes square root of 12 over square root of 49. I'm going to do the bottom part first because that's the easy one. Square root of 49 is 7. Now 12, I'm going to rewrite it and think, what times what is 12? Such that one of those numbers is a perfect square? Well, 4 is. 4 times 3. And the square root of 4 is 2, and the 3 stays. And the 7 stays on the bottom, so the final answer is 2 square root of 3 over 7. And we're done with that example. Well, let's simplify some radicals that have variables now. And once again, we're assuming these are positive real numbers. The variables represent positive real numbers. So start with this first one, x to the 11th. I'm going to do this one the long way. And then I'm going to show you a really shortcut way. So the first thing I'm going to do is rewrite x to the 11th as square root of x times x times x times x. I'm going to write 11 times. How many do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now, every two of these means that I have x squared. Now you could also use exponent rules if you want to do it a whole lot quicker, but that's not the shortcut I was talking about. I like doing it this way so you can see exactly what's going on. I'm going to separate each one of these with its own square root. And now, since the variables represent positive real values, each of these square root of x squares represents a plain old x. Now you notice this last one, it stays underneath the square root because it wasn't x squared, it was just the square root of x. And you'll notice that I have 5 x's on the outside, and when you multiply those, you do get x to the 5th, and then the square root of x stays. So your final answer is x to the 5th times the square root of x. And here's a shortcut way. You'll notice that x to the 11th consists of 11 x's. So what you really are finding is how many x squares are there in x to the 11th? Well, there's 5 of them. Right there they are. And each one of those comes out as an x. So that means that you end up with an x to the 5th, because there were 5 x's that came out. And you end up with x to the 5th on the outside and a single x on the inside. Well, here's a shortcut way. Shortcut way is to take the x to the 11th, square root of x to the 11th. Notice that the number on the outside is a 2, which is actually the same thing as x to the 11th over 2. Now if I come over to the side somewheres, or just below, let's go to the side. And if I divide 2 and 11, we get 5. 5 times 2 is 10, the remainder 1. What that means is that I have 5 x squares that come out, which means I have 5 x's left over, or that come out, and this remainder of 1, which stays underneath the square root. So, what you're doing is you're dividing the 2 and the 11, 5, and you get 5 times. That goes on the outside, and the remainder is the exponent of the radicand on the inside. Shortcut. You can do it the long way, or you can do it the short way. However you want to do it. I, for one, want to do it the short way. So, for example, let's do f part. First thing I'm going to do is I'm going to separate these using the quotient rule. Is the square root of x to the 9th over the square root of 4 y to the 4th. And then what's going to happen is I'm going to do the bottom part first because it's easier. The square root of 4 is 2. The square root of y to the 4th, that 2 goes in the 4 2 times. Now, on the top part, the 2 goes in the 9 4 times, and then my remainder is 1, and that goes on the x on the inside. 2 goes in the 9 4 times, the remainder of 1. Shortcut way, the way I prefer to do it. And we can even expand that to include any index or any root. So let's do this one. First thing I'm going to do is I'm going to do it all at once, just so you can do them all at once. I know that the 4th root of 625, if you use your calculator, you'll find out the answer is 5, because 5 times 5 is 25, times 5 more is 125, times the 4th 5, which gives you 625. But I also know that 4 won't go to 11 evenly, so that means that I'm going to have some variables under the 4th root and some outside the 4th root. Now notice, make sure you get that 4th root in there. Here we go. And I'm going to have some x's on the outside and some on the inside because 4 doesn't go 11 evenly. In fact, 4 goes 11 twice with the remainder of 3. Because 4 goes into 11. If you count by 4, it goes 4, 8. It goes twice with 3 left over. Now I also know that 4 won't go into 21 evenly, so I got some y's on the outside and y's on the inside. So 4 goes in 21 5 times, the remainder of 1. I'm not going to write that 1, so I'm done. Just by dividing and making sure that my quotient goes on the outside exponents and my remainder are the inside exponents. And that's it. I know of no easier way to do those.